But of course, if you want to check if two vertices are connected, then lists could take long. Okay, so as you would imagine. Well, adjacency matrix is very fast. And we also saw this notion of connected components and strongly connected components. Okay, and for directed graphs, we said the notion of connected components is more tricky, and we defined this notion of strongly connected components, okay, where you reach U from V and V from U. And so we also saw depth first and breadth first search. So just to recap, okay, so depth first search is, so here the goal is you are given some vertex and you want to find everything reachable from V in this graph. Okay, so for this, it doesn't matter if the graph is directed or undirected. Then what we did was you initialized, so this was a natural recursive algorithm, and we initialized this reachable to be false for everyone except the vertex itself, and then you do the search starting at this vertex. Okay, so for every vertex in the neighborhood, you basically go to all its neighbors and set reachable to be true. And if you haven't visited it before, then you recurse on that. Okay, so starting at the neighbor. So we saw in what order you explore a tree given this. Okay. And by the way, so if I'm sure most of you have seen DFS before, but if you haven't, if you want to have a nice visualization, there are websites. Okay, so just Google good visualizations of depth first search. You'll find some pictures. Okay. And then this was breadth first search. So it's a different way of doing the same task. Okay. So you want to find all vertices reachable from V, and you also want to keep track of the distance. Okay. So you want to explore vertices, but in the order of their distance. Okay. So that's the example. So you're starting with 1, and then you see 2, 3, 4, and then you see the next ones and so on. We said that you can achieve this kind of a search by maintaining a queue. Okay, so we said, so this is the code we saw last time. So you start off with the same kind of initialization. You said reachable to be true only for V, and additionally you have this queue which we call Q. Okay, and as long as this queue is non-empty, you take the first element of the queue, okay, and for all its neighbors, check if it was already reached, and if they were not, then you add it to the queue, to the back of the queue, and you continue. Okay, so this way we said you're guaranteed to explore things in the order of their depth. Okay. Depth meaning the distance from the root. So today we'll start off by seeing a slight extension of this, where you have weighted graphs. Okay. So you want to do the same thing. So you want to, explore the graph and also keep track of the distance from a vertex V. But now you have weights on the graphs. Okay. So we saw a similar example last time, where so let's say I want to start off. So this is the V. This is the node I want to start exploring from. Okay. Now, if you do a regular, if you do a breadth first search based on the number of hops, like we were doing before, we said that maybe you don't find the shortest distance. Okay. So, for instance, if you try to look for the shortest distance from V to this U, okay, to this last guy, then that's not the shortest one, because we are actually interested in a weighted shortest path. So it's the path which takes 3 hops is actually the right one that we want to find. Okay. So this is why on weighted graphs you have to be a little bit more careful. Okay. Okay. So let's. This new path has more hops, but has smaller total distance. Okay, so for this, we're going to see this algorithm called Dijkstra's algorithm. This is something most of you would have seen before. So how many of you have not seen Dijkstra before? Okay, how many of you have seen? That's probably easier. Okay, so okay, I see some shaking, which means it's good to redo it anyway. So, all right. So the goal in this algorithm is to essentially find shortest paths from all starting from a single vertex. Okay, so that's why this problem is called a single source shortest path. And this is a natural extension of breadth first search. Okay, so you want to keep track of Q like you did in breadth first search, but you have to be more careful with these weights. Okay, so that's the idea behind Dijkstra's algorithm. Okay, so let's say we start off with this assumption that we want to mimic breadth first search. Okay, so you have this graph and you want to mimic breadth first search here. So let's start with this vertex. Okay, so you see its neighbors, this guy and this one. Okay, so you see these two neighbors. So if you want to mimic breadth first search and then continue processing one of the neighbors, so which one should you process first? So you would want to do this guy first because, I mean, in some sense, he has the shortest path from V, right? So you know that, I mean, okay, assuming that this weight is, let's say, 6. Okay, so assume this weight is, let's say, 6. So these are the neighbors and this is the shortest one. So if you want to find the shortest paths out of this vertex, then you really want to start exploring this guy first. And you're guaranteed that for this vertex, so let's call this W, the shortest path from V to W is actually 4. Okay, so I've got to say one thing here. So I'm assuming that all weights are non-negative. Okay, so that's an important assumption. So we'll see what happens if that fails in a bit. Okay, so I want to claim that so the shortest path from V to W is actually 4. Okay, so why is that?
It's the smallest weight.
It's the smallest weight edge, sure, but I can't say the same about that 6 edge, right? So I can't argue that the shortest distance from that to V to that vertex is actually 6. Because for all you know, there's a shorter path like this. Okay, so maybe if this is 1, then this is a path of length 5.
So it's because all the other paths off of V are higher.
Are actually higher. Okay, so any other edge out of V is actually of higher cost. So this guy we are guaranteed that it's the shortest path. Okay, so this is one reason you might want to start off by exploring with this guy. Okay. So if you want to, so this is, so you want to process neighbors in order of increasing distances. Okay, so this makes sense. And so if you wanted to modify breadth first search algorithm, then what you might think is, okay, so I have this queue, which is the nodes I want to explore, and I always keep them sorted. Okay? So this is a natural idea. So let's say we try doing that. Okay? So there's another catch that you have to take care of, which is that, so earlier, there was no question of adding a vertex to a queue twice, right? Because you were always going in increasing order of the depth. Okay? So if you saw that a vertex was already visited, you could just safely ignore it, right? So if you remember the code here, so if reachable was not false, then you did nothing with that vertex, right? So here you can't afford to do that because even though you have reached a vertex, maybe you haven't reached it using the shortest path. Okay, so here reachability is not the point; it's the distance that you've taken to reach this point. to reach this vertex. Okay, so that's the thing that matters. So, okay, so what this suggests is maybe you have to keep track of the distances you have taken so far to reach different vertices. Okay, so let's see a natural modification of breadth first search. Okay, so instead of reachable, remember reachable was a Boolean array, right? Instead of this, you now have a distance array, okay? And you initialize it to infinity for all vertices except v. Okay? So remember, we are trying to find the shortest paths out of v. Okay? So you initialize distance of v to 0. Okay? So this is the same kind of initialization that we had before. And then you have this queue. Okay? And then again, you take the first element of this queue. For every neighbor, now instead of actually checking if you've already seen that vertex, you now see if going through this vertex u actually gives you a shorter path. Okay, so what you're checking is, so this is the v, and you have some u out here, okay, which is the vertex that's currently on the top of the queue. Okay. And for every w, you're checking, you may have had some value for distance from v to w. Right? So this is, initially it would be infinity. Okay? But otherwise you may have found some path, and maybe w is already in the queue. And so it has some value. So what we are doing here is checking if going via u is going to give you a shorter path. Okay, so what I'm saying is, if this distance from v to u plus this weight of the edge uw, okay, so if this weight is strictly smaller than the current distance to w, okay, so this is the current value you've got, then you've got to update that current value, right? Because that's not the right distance. You have found a shorter path. Okay, so it's a natural idea. So you basically you can also think of it as a dynamic programming thing, as a dynamic programming algorithm where you keep track of the tentative shortest paths. Okay, this is the shortest path you found, and that is stored in this array. And every time what you do is you basically check if you can do a shortcut. Okay? So this is what you're checking here. So if going through from v to u and u to w is actually shorter than this, then you update this distance. Okay? And every time you update, you push this vertex w into the queue. Okay? So it's a natural algorithm. But remember what we said was, you've got to process things in the increasing order of distances so far, right? So after every iteration, you have to sort this queue, okay, by using the distance values. And this is an important step because remember we said that you always want to see the vertex with the smallest distance so far and then process that guy. Okay. So is the algorithm clear? So what the algorithm is, not the correctness. We'll see the correctness in a bit. But so the algorithm is basically every time, so you maintain a queue just like you have in DFS. But now the key thing is you distance values. Okay, so the entries of queue are the vertices, but the sorting is done by this distance values. So that's something to keep in mind. And every time you take the element which has the smallest distance value, that's the front element of the queue, and then you try to see if that could be used to get some shorter distance. Okay, and if so, you just push them back into the queue. Okay, so this is a very simple algorithm. And notice that this is almost the same as breadth first search, except that you might add elements to a queue multiple times. Okay. I mean, you might consider adding them multiple times. If it's already there, you don't physically add it, but the distance value gets updated. Okay. So this is the algorithm. So why is this correct? Okay, so how would you prove that this sort of an algorithm is correct? Any guesses? So proving any algorithm, you would say, okay, induction, right? So but induction on what? So how would you? Actually, we'll prove this algorithm in a slightly different method. But how would you reason about such an algorithm? Yeah.
Maybe an intuition if we're trying to get from A to C, if we know the shortest from A to B is like the shortest possible, and maybe the shortest from B to C is also the shortest. So you can kind of
yeah, so that's kind of right. But what I want to do is essentially reason like we did before, right? So remember in the original in the picture that I showed before, we said that the shortest path from one vertex from V to W has to be the right one. Okay. The way we said it is by saying every other edge was actually bigger and there were no negative edges, so this has to be the shortest path. Okay. So I want to extend this argument, okay, and keep saying that this has to keep happening. Okay. So note that the procedure is kind of trying to do this, right? Every time it picks the smallest element in the queue so far. Okay. So what I want to claim is that every time you do this loop, so the algorithm has this while loop. Okay. So every time you do this loop, I want to claim that the element at the front of the queue. Okay, so this is that vertex. I think we called it U. So this has the correct distance value. Okay, so correct basically means the distance of U at this point is the true distance in the graph between V to U. Okay, so is this claim clear? So we are looking through how the algorithm is executing, okay. And what we are saying is, in every iteration, you have some queue, you have some element at the front of the queue. Okay. So this is basically the vertex that has the shortest dist value. Okay. We are claiming that that distance value is actually the correct distance value. And I want to claim that this continues to hold throughout the execution of the algorithm. Okay, so that's the claim I want to make. And remember that in the first few iterations we already did this. Okay, so this you can try to prove by induction, right? Because you can say that initially your queue just contained the vertex V. Okay. So for this, the statement is clearly true. Okay, because the dist value is 0, true distance is 0 from V to V. Okay. And then what we are doing is exactly what we saw before, right? So we had 1, 5, 4 and 6. We added them into the queue and then we sorted them. So we got, now the queue contains these 3 elements, and this is the first, this is the second, and this is the third in the queue. Okay, so they are in this order. So next time we'll end up processing this guy. Okay. And for this guy you now have the guarantee that you have the shortest path. That you have the correct dist value. We want to claim that this continues to happen. And so is the statement of the claim clear? If you have any questions, feel free to ask. So the way we prove this claim is by showing an easier claim, okay, and this is the following. Okay, so what we are saying, so when could this not happen? right? So when could the distance value at the start of the queue not be the right one? So the only way it cannot be the right one is if there is some path that, so we have this vertex B, and let's say the front of the queue at some point is U. Now the only way that the distance value is not correct is if there is some other path which we have not seen yet. Okay, so this is going to show up later, and somehow the distance from V through this path is actually shorter than the distance that you've had so far. And the only way that could happen is if this vertex is somehow processed at a later stage, okay, and then you see this edge, okay, from this to this. Okay, so this is the true shortest path. Okay, so you see this vertex at some stage, and then you process this edge. But I claim that this can't happen. Okay, so the reason is that the distance value for this guy, the true distance, is actually shorter than the true distance from V to U, right? Because the shortest path from V to U goes via this vertex, and the edge weight of this vertex is non-negative. So this has to have happened before it could happen. So this is essentially the kind of claim that we want to make. And more formally, what we will say is, as the algorithm progresses, the distance value, okay, so this is the distance in the array, this value of the element in the front of the queue, so of the front of the queue, is non-decreasing. Okay, so it only increases. Okay. So is this? So this claim has to be very easy. Okay, so to see. So anybody see the proof? So we are claiming that. So you have this while loop. Okay, and this is going on, and then these dist values are getting updated like this. The claim is, as this loop proceeds, the dist value for the element at the front of the queue always keeps increasing. Okay, so why is that?
Because your queue is sorted.
Well, the queue is sorted, sure, but so you have to say that, yeah, you never update it so that you become smaller than the smallest element of the queue. And that's actually clear because
there are no negative edges.
exactly. So there are no negative edges in the graph. So if you had if you take the vertex with the smallest dist value so far, then it always has the right distance. Okay, so there could not have been, you can't use the dist value of some other vertex, use one of the edges to get a smaller dist value. Okay. So that's what's going on here. And this is basically the key idea behind the proof. Okay, so and this ends up showing exactly what we want. Okay. So yeah. So I don't want to get into the full details of the proof, but this is the rough idea. Okay, so you basically claim that in every as your algorithm progresses, the dist value of the first element in the queue is always increasing, and which means that the value is actually the correct distance. Okay. And now so this means that in every iteration you get one vertex and you get the correct distance for that vertex. Okay. So how many iterations could this algorithm have?
Number of vertices.
Yeah, so basically you can't see any vertex twice, because once it has reached the front of the queue, you know that you've computed its true distance value. Okay, so there's no way you'll reach it twice, because I mean all edge weights are non-negative. So you will not reach any vertex twice, and this is why the running time, so the number of iterations of the loop is less than or equal to n. Furthermore, you know that loop executes at most once for each vertex. Okay, so that's one time. Okay. So for every vertex you execute this loop. I mean, in the sense that u becomes that vertex at most one time. So this is a clean guarantee. So what's the running time of this? So I've said that this loop executes at most once for every vertex. But so we have to go step by step, right? So that's the only way we know how to analyze algorithm. Okay, so let's see. So this, how long does this take? So this is, you want to find the first element of the queue. So this is just constant. And okay, and now you have this for loop which loops over all neighbors. So it runs degree of u times. And each time, how long does this take? So there is this step which we have got to worry about, right? So we are adding w to this queue if it's not present. So how long could that take? If you had a regular queue, how long would it take? So this is just a constant time if you have regular queue, right? Because you just add, I guess you have to do some search to see if it's not present or not, if it's present or not. But let's say you can do that, then it's very easy, right? So then it's constant. But note that there is this weird step of sorting the queue. Okay, and this is unfortunate, right? So this will take size of the queue log, n log n steps, where n is the size of the queue. And this is bad for us. Okay, so this sorting is unfortunate. So the queue could have size as big as n, and this could take roughly n log n steps. And this is still in the loop. Okay, so overall you get only a bound of n squared log n. Okay. So this is even assuming that this addition and stuff take only constant time. So this is, yeah.
But you're only adding elements to the queue if the distance is smaller than all the other elements.
Yes.
So when it's already sorted, why would it sort again?
No, it's not smaller than all the other elements, right? Because
Smaller than the first element, but the first element is smaller.
right, but so consider this case where you have, say 4, 5, 6, and you have this edge 3. Okay, you have one edge 3 and one edge let's say 2, or let's say 1.5. Okay. So what you'll do is you'll first start processing this guy, then you'll start processing this guy. Okay. Now when you see its neighbors, okay, so this guy has to be added in the middle of the queue somewhere, because your queue already had 4, 5 and 6. Okay, so your queue had 4, 5 and 6, and now you've got this guy with a candidate distance of 5.5, with a dist value of 5.5. Okay. So you've got to add this 5.5 between 5 and 6. Okay, so
But the distance of that point is 5.5,
which is not what? Yeah, maintained in terms of the global dist values, right? And you don't know where you've got to add it. So one way could be maybe while adding it, you are more careful and you actually figure out the right place in this sorted array. Okay, but that itself takes a linear scan, and that would end up taking over n time. Okay, so overall, there's no easy way of avoiding n squared like this. So is the question clear? It's a very good question. So so his thing was, why is adding to the queue not trivial? Okay, so you might have to add somewhere in this sorted list. Alright, so how do we avoid this, right? So this is, for those of you who have not seen these kind of things, so what we are looking for is a clean data structure. Okay, so what we want is some kind of a data structure, and it's supposed to, so a data structure is basically something that allows you to store various elements. Okay, so elements of various form. So in this case, what we want to store are vertices, and you have this dist values, okay, for these corresponding vertices. Okay. So these are things that you want to store in this data structure. And what are we doing, right? So we keep adding vertices, okay, and you have its dist value while you are adding it. So this is one operation that we have to allow. And we are also updating the dist value. Okay, so sometimes, so if the dist of w is bigger than this, then you are setting this. Okay, so sometimes we are updating the dist values of the vertices that we've already seen. Okay, so that's one thing that you've got to support. Okay, so that's one thing that you are interested in doing. And sometimes you're adding new elements. Okay, so that's the first thing I said. And the most important thing is you're often, every time you're picking the element of the smallest dist value, you're removing it from this data structure. Right, so this is, so these are the three operations. So this is one thing that you've got to keep in mind when you are, in general, coming up with data structures. You have to figure out what all operations you want to support. Okay, so you want to have a data structure that stores these elements. So you have to figure out what you want to store and what operations you want to support. Okay, so here we want to store things like this. So we have pairs v comma dist of v, and we want to support operations of this form. Okay, so, and sometimes you might want to go back into the algorithm and see, do we really need all these things? Okay, so in this case it turns out that if you're able to do this and this, it's actually not so bad. Okay, so you don't have to update, you can just add something twice. Okay, so let's not go into that, but let's actually see a data structure which tries to support all three of these. Okay, so this is, I'm doing this because I also want to recap a little bit about data structures. So let's do that for a bit. Okay, so we want a way to maintain tuples of this form, v and distance of v, and you want to support all these things. So let's say one could do all of these operations in time, I don't know, in some O of, just for an example, let's say I can do it in all constant time. Then what would the running time of the algorithm be? So suppose I had a magic data structure that allowed me to do all these operations in constant time.
Same as breadth first search.
Yeah, then it would be exactly the same as breadth first search, because this takes now O of one time, and now I don't have to do this at all. Okay. And here we are just doing this min operation, right? So find the min element, and this are basically you're finding the minimum element and removing it from this data structure. Okay. So these two we said just take O of one time, and this one takes O of one time. Okay. So now this is exactly the same running time as breadth first search, and this is basically O of m plus n. Okay, so this is great. But it turns out that that's too much to hope for, and what we can actually do is something like O of log n for each of these. Okay. So, does anyone know how you can get this kind of a running time?
Balance tree.
Yeah, balanced tree of what sort? Yeah, so that's the kind of thing that we'll go for. Okay, so we want so what are called binary search trees. Okay, so for those of you who've seen it, hopefully all of you have seen it. So this will be a quick recap. Okay, but this is a data structure that everyone should know about. Okay, so and it's in some sense, if you know this, you can kind of figure out the rest. Okay, so I mean. That's an overstatement, but you can figure out a lot of other simple enough data structures. So let's see. So suppose you have a collection of integers, and you want to store them. You want to store them in some structure. And what you want to quickly do, our query, which is given some integer, you want to find out if it exists in this data structure or not. And sometimes you may want to add or delete. Okay, so you might want to add an element or delete it. And all these things should be done fast. Okay, so in this case, something like O of log n time. And so binary search trees are a very simple data structure that allow you to do this. And the idea is extremely simple. Okay, so integers are completely ordered, so you can compare any two integers. And what you do is you maintain a tree, okay, where you have a node. It's called a binary search tree because it's a binary tree. Every node has two children, except the leaves. So you have some tree of this kind. And the elements of the things that you want to, the elements you want to store are actually stored in the nodes of this tree. Okay? And you want this nice property that if you take the root of any subtree, okay, so you take any subtree, you could have taken the full tree for example. You take the root of this tree, the root stores some element. So it stores some element A, and all the elements to the left of A are smaller than or equal to are all smaller than or equal to A, and all elements to the right are bigger than A. So this is what is called a binary search tree. And it turns out that you can always, I mean, think about it for a bit, you can see that you can very easily create binary search trees. But the important thing is you want these trees also to be what is called balanced. Okay, so you want the depth of this tree to be small. Balanced trees. And once you have all your data stored with this property and in the form of a tree, then you can easily see that doing all those operations are actually relatively quick, fast. And it turns out that there are nice ways of doing this. Okay, so there are nice ways of maintaining the balance, of maintaining always a depth of roughly O of log n. So this is a data structure that all of you should know, and if you haven't seen it, you should go read up about it. Okay, so the important thing is this. So you have a collection of objects that are all completely ordered. You store them in a tree of small depth. You have this property that the root of any subtree has the element smaller than it on the left side, elements bigger than it on the right. Okay. So this is the important thing about a binary search. Okay, so how do we use them in our problem, right? So what we wanted to do was support these three operations, right? And our objects were actually these pairs of v and distance of v. So this is a little bit odd, right? So in the standard thing we said that we only have integers, okay? And now you have these tuples. So how do you come up with a complete ordering of tuples? So is the question clear? So you want to say that, so you want to store tuples in a binary search tree. Okay. So here the nodes are not just integers a, but you actually have things of the form v, comma, distance with v. So yeah, that's correct. But let's see if so have many of you seen this? So if you have objects that are not integers, okay, and you want to define a total order between them. Okay. So this is a very helpful thing. Okay, so this is something you might want to do a lot of times because exactly for things like this, you want to store things in a nice data structure. So it's nice to be able to compare all of them. So what do we want from our data structure, right? So we want to find the element that has the smallest dist value. Okay. So in some sense we want that element to be the smallest. Okay. So how would you try to define a comparison between two elements? So suppose I gave you so recall that these are like v comma dist of v pairs, and I give you a node u with distance 2, node u prime with distance 3. So which of these would you say is smaller? So when you sort in the queue, I mean, let's say you sort all these tuples. Yes. So which one would you want to be the smaller one? Yeah, the one with distance 2, right? So because we are interested in finding the element of smallest distance. So then you could say, oh, okay, so then what if you had u2 and u prime 2? So this is a little bit of a degenerate case, but you have to distinguish between these two, right? Because they are different things. So how would you compare them? Yeah, I think your expression says it all. You can do anything, right? So I think, yeah, you know, anything is fine, right? So you can just have a lexicographic ordering, or you have some, you know, use our indices of vertices, right? So they'll have some ordering between them. So just take any order. Okay. So if u prime less than u, then say that this is smaller, otherwise say that this is smaller. Okay. So you can break ties in any way, but in a consistent way. Okay. So this defines an ordering for pairs. And once you have this, you can now convince yourself that firstly, this is very easy, right? Because the least element you can always find very quickly, and this you can just remove. Okay, and this you can remove in time, which is O of log n, because that's the height of the tree. So I haven't told you how a binary tree search tree does it, so it might not be clear, but if in a binary search tree you could remove the smallest element in O of log n time, then even for our data structure you can do it. Right? So this is what we want to do. And you can also think a little bit about how you do both these operations. Okay, so this is a very simple exercise, so I won't go into the details. So whenever we update the dist value, the only thing you have to notice is whenever we want to update a dist value, we know both the old and the new values. Okay, so it's important that you know the old value because that will help you find the node in the tree, and then you can go ahead and remove. So this is, I'll let you think about this. So this is an easy, some observation here is when we want to update. We know the old and new. Okay, and the first thing turns out to be extremely easy because that's just inserting into the binary tree. Okay, so yeah, it turns out you don't really need the full power of binary search trees. You can also do this with what are called heaps. But we won't get to that. Okay, so it's anyway good for you to know binary search tree. Also, these are implemented by default in languages like C++. There is this notion of set. I don't know if all of you know this, but yeah. So C++ has this standard template library, and there is some notion of set, which is basically an implementation of a binary search tree. So you don't have to implement anything. So to do Dijkstra, that's the easiest way of doing it. Okay, so RQ has a easy implementation in terms of binary search trees. And so what's the final running time? Oh, okay. I forgot to copy paste the algorithm. But basically, so you have this. Now you no longer have this sorting step, and we said that each of these operations. One is finding the first element and popping it. So this we said can be done in O log n time. This is using binary search trees. And all these additions and updates, each of these take time O log n time. So if you think about it, it will end up with overall running time. M plus n times log n. So it turns out this is not quite the best one can do. You can actually get the m out of the log n. So you can get over m plus n log n. We won't go into that. But this is, for most practical purposes, this is reasonably fast. Okay, so any questions about the analysis? I skipped over some of the parts, but they are figured out on your own, so I didn't spend too much time on it. So any questions about it, I'll be happy to answer. Okay, so alright. So far, I mean, the algorithm we described, it uses the non-negativity of edges very crucially, right? Because what we said is, once an element reaches the front of the queue, then you have found its shortest path. So that was the key to the analysis. Now, what if you allow edges to be negative? So for instance, let's say you have the same kind of edges. So you have 5, you have 4, you have -2, maybe you have -3 here, and you have 2, 1. Okay, so something like this. So, is there any really serious problem that could happen? Like here again, you want the smallest distance, right? So from, let's say here to here, you want to find the smallest distance. So you could try all paths, and maybe you can find the smallest, right? So is there any real serious problem that could happen? Sorry? Oh, yeah.
Just keep cycling.
Yeah, so this is what he said. So basically, so what you're saying is maybe suppose I want to get from this vertex V to W. So I could always, I could do this, and this has value 3. But then what if I just looped around? So the thing to notice here is that there is this loop which has total edge weight minus 1. Okay. So now I could just say, oh, okay, I'll actually loop around once, and then take this 4 and minus 1, and then I'll have the distance being 2, right? And I could loop around twice, and then it will be 1, and so on. Okay, so you can keep looping. So this is clearly you can't hope to do anything in such cases, right? So if there's a vertex, if there is a loop with total negative weight, which involves B, then the distance can be minus infinity. Okay, so the distance basically minus infinity, it's not well defined. Okay. But suppose this does not happen. Okay, so assume the graph has no negative cycles. So the question is, how can you find shortest paths? You can also ask the question, how do you tell? Is there a good way of telling if a graph has negative cycles? Okay, so that's the other thing you could ask. Okay. So let's consider both these questions. Okay, so first, assume no negative cycles. So what I want to claim is, the first observation, it's a very simple one, is for any u and v, I claim that the shortest path has length at most n. If edges are non-negative, this is obvious, right? You can't have length more than n. But even here, claim that the shortest path cannot have length more than n. Why is that? Like, what if it had length more than n? Yeah, this is a big fool. So I'm saying you have n is recall it's the number of nodes. Okay, n is the number of nodes, and you have some u and v, and could you firstly, if you have a path of length more than n, okay, so could it have all distinct vertices? Like there are only n vertices total, right? So you can't have more than n distinct vertices. So any path of length more than n has to have at least a cycle. Okay, so it has to go through some vertex twice. Okay, so we can do that. So it will look like you go through something twice. Maybe you don't reuse this edge, but you go like this. So this doesn't exist. So path is something like that. Okay, so you reuse that vertex. Okay, so you're reusing this vertex. This is why it has.
Are you assuming that the weight is 1?
No. So length here is actually the number of hops. It's not the sum of the weights. Yeah, so it's okay, so it's actually the number of nodes in the path. So yeah.
Just clarifying point. So if we had been talking about cost, that would be the way to get this, but length is strictly just the number of hops.
So yes, this is how I'm using it. I don't know of a better. You have a better word for
No,
it.
just making sure.
Yeah, I don't want to use distance because distance has the length, has the weighted connotation. So I thought length is, one could say size, I guess, if you really want. But size of a path sounds odd. Okay. So anyway, yeah, so if you have a path with more than n nodes on it, then at least one node has to be repeated. Which means it looks like this. And now, what is the total weight of this cycle, right? So this total length of, we assume that there are no negative cycles. Okay, so the total weight of the edges on the cycle, they have to add up to something. They cannot add up to something less than 0, okay, because there are no negative cycles. Okay, so the total weight of edges on this cycle is bigger than or equal to 0. But then why do you have this cycle in the first place, right? So that's the argument. Okay, so chopping off this cycle and just taking the path that looks like this to be is at least as good as this other path. Okay, so this is the proof. Okay, so if you want to be really formal, you have to say that for any u and v, there exists a shortest path between u and v with length smaller than equal to n. Maybe the cycle has length equal to 0, in which case you could have it or you don't have to have it. So that's just a minor point. Okay, so this is an easy observation. Okay, so if you have length is smaller than equal to n. So now we are going to see what is called Bellman-Ford. Apparently it was first introduced by someone called Schimbel, so it's also called Schimbel's algorithm. So as you will see in these kind of early graph algorithms, I think a lot of people invented them. So there's always this question of credit. Okay, so who you give the credit to? But classically people call this the Bellman-Ford algorithm. So we'll call that. Okay, so before we go on, so I want to say one other thing which I didn't quite emphasize, which is directed versus undirected. Okay, so once you introduce negative edges, the distinction between these two becomes more prominent. Okay, so there's this. Okay, so without negative edges. If you had a graph without any negative edges, then solving on undirected graphs is a special case of directed graphs. So now that you've all seen reductions, it's like undirected graphs are less than directed graphs. Okay, so if you can solve it on directed graphs, you can solve it on undirected graphs. And the reason is just you can replace any edge with two edges. Okay, so if you just had non-negative edges, if you had an undirected edge, you could replace it with two directed edges, and it works. It works well for the purposes of computing shortest paths, because in some sense you can traverse this edge in either direction. So you have this. Okay. But the moment you introduce, you had negative edges, then this becomes a negative edge cycle, negative weight cycle, and this causes all kind of problems, right? So this now allows you to loop around and so forth. Okay. So you can't use this twice. Okay. So it turns out dealing with undirected graphs with negative edges is a bit more tricky. Okay, so we won't do that. So for now, let's assume that our graphs are directed. So this is one of the few counterintuitive places where undirected graphs are actually trickier than directed graphs. Okay, so usually for most graph problems, directed graphs are the problematic case. Even there are a few cases where it makes it easier if it's directed. So does everyone see the issue that if you don't have negative edges, both are equivalent. But once you have negative edges, it's you can't do this reduction. So undirected graphs are a bit more tricky to handle. Okay, so we'll assume that graphs are directed. So now let's say you have a directed graph and it has potentially some negative edges. So that you have this graph, it has edges 1, 2, -1, -4, 2. And you know it has no negative weight cycles. Okay. You also know that it has no negative weight cycles. And we want to find shortest paths between vertices. Okay, so let's say I want to find shortest paths starting from some vertex. Okay, so the same problem as before. Now, so before I do this, what I want you to think about is, suppose I tell you, find all shortest paths of length at most k. Okay, so length is the number of hops. Okay. Suppose I tell you find shortest path between A and D, or A and let's say E. Of length at most 1. Okay. So what is the shortest? There is no path, right, of length less than equal to 1. So the shortest path length is infinity, right? So shortest path width cost is infinity. But if you have length less than equal to 2, then you know that the cost is -2. Okay. So this is the quantity I am interested in. Okay. So, and if I allow shortest paths of length, let's say less than or equal to 10, then maybe I could also have considered this path. Right? Although it turns out it's longer, but still, I could. That's a feasible path. Okay. So we are interested in computing quantities of this kind. Hopefully, all of you have been doing dynamic programming homework. So this sounds very dynamic programming, right? So what you're saying is, I mean, you have this parameter k, and you know, let's say k is 1 or k is 0. Okay, so if k is 0, only vertex A gets some value. So vertex A gets disk of A comma 0 is 0. The rest of them have disk of B comma 0 is infinity, and so on. Okay, so we're always interested in distances from A. Okay, so maybe you want to write disk A. So can we come up with a recurrence? So we want to maintain these quantities, dist A of U comma K, and formally what this means is shortest path from A to U of less than or equal to K hops. Okay, so this is the quantity that we want to compute, and so how would you develop a recurrence for this? So I have A and I have U somewhere out here. This is simpler than some of your homework problems. So you want, I mean, at most k hops, right? So if k is 1, what would you do? So this is how you can usually think about things. So you want to think of general k. So what if k is 1? Yeah, so if you have distance 1, then any u that's not a neighbor of a, so that doesn't have an edge from a to u, gets value infinity immediately. Right? So anybody, and if it is a neighbor, then the only length 1 path is just the direct path. So the weight of that edge is the shortest, is this dist a is the shortest path. Now, what if k is slightly bigger? So what if k is 2? What would you do? Yeah.
So if we know the distances from the neighbors of A to U with k minus 1 length, then we add the weights to those distances.
Yeah, so what he's saying is, look at all vertices that have paths of length k minus 1, okay, from A. So this has k minus 1 hops. Okay. So this is a path of length k minus 1. And from here maybe there's an edge to u. So this is the only way you can end up with a k hop path from A to u. Right? So you do k minus 1 hops, reach somewhere, and then you go to u. Right? So that's that. Okay. So and then you could say, okay, so try all vertices that have. So I guess this is what you're suggesting. Try all these such that this A of u k is not infinity, and then do set min over how what is it v. Weight of v to u. Okay. So go to some vertex v using k minus 1 hops and then take the path. Okay. So that's what. So this is a natural thing. And you should also consider this thing of k minus 1, right? Because our definition was using a path of less than or equal to k hops. Okay. So that's fine. So this is a natural way of finding distance to u. Okay. So this is correct, but can you do slightly better than this? Do you really have to go through all vertices v? I mean, suppose you had just an n degree of 2. Then you know that there is no direct edge from anybody other than these two vertices to u. Right? So this weight would be not defined. Okay? So you can just look at vertices that have edge to u. And so this process, I mean, you could also say try all vertices v that have an edge to u. And then you can do the same process. So how long does this take? So how long does each recursive step take? I mean, suppose I want to find for one u. I'm only looking at the neighbors, right? So, and I'm looking at things that are already computed. maybe some people are lost. So, but it's I'm asking actually a very simple question. So what I'm saying is, so the update, the way the update is happening is, you want to compute distances from A to U using at most k hops. The way we are doing it is by saying, I look at all vertices that have, all vertices like this, okay, that have an edge to U. Then I'm saying try to look for a k minus 1 hop from A to these vertices, like one of these vertices, and then you take an edge, right? And you take the direct edge to U. That's the only way you could have a k path. And the shortest distance from A to these vertices, using at most k minus 1 paths, have already been computed. Okay, because it has this k minus 1 parameter. So suppose they were all computed, then how long does it take to compute this quantity? It's just, yeah, the number of vertices that you check, right? So which is the in degree of U. So, okay. So having computed these values for all k minus 1, the amount of time it takes to do this for every v is, for every u, is sum over u in degree of u, which is basically the number of edges. Okay, because this is a directed graph, some of the in degrees always add up to the total number of edges. Okay, so this is for every, assuming you've computed for k minus 1, how to do it for k, right? So, and until what k do you have to do this? So k is, remember, the number of hops, right? So what we are saying is compute these quantities for every u and for every k. What we are actually interested in is just the shortest distance, right? So that's like saying k essentially tends to infinity. But we said some time ago that k could not be more than n, okay, because otherwise there has to be a, assuming there are no negative weight cycles, you can assume that k is at most n. So this is all there is. So it takes time, n times size of E. So this is a simple algorithm, and it takes time of n times E, and maybe we'll stop here, but next time we'll see how you can, in some sense, make these faster, do other related things. If you have questions about this, just let me know, because some of you maybe you're seeing this for the first time, so it's good to understand these well.
Do you know when you'll be posting grades from board one?
Sorry?
Do you know when you'll be posting grades from board one?